Hello everyone, and welcome to the first edition of Daily Coding Challenge, where I'm going to pick a random LeetCode problem, and I'm going to solve it live. Alright, let's get started. So, we're going to go for a hard difficulty problem. Got it sorted by the acceptance rate, just so we can work our way towards the even harder problems as time goes on. I already did this one, and I've done this one, so okay. Let's move on to this one. Minimum number of flips. Let's read through the problem. All four of the neighbors, if they exist. Interesting. The minimum number of steps required to convert a matrix to a zero matrix, or -1 if it's impossible. Interesting. So right off the bat, I guess the brute force solution that I'm thinking of is that, you can explore every single possibility, and then from that possibility you can explore every subsequent possibility. And this way you can find the smallest number of steps in order to get to a solution. Now, of course, that is a brute force solution. You can use some dynamic programming techniques to keep track of, given a certain matrix, is there a solution, or what is the solution given a certain matrix? That way you avoid having to recompute things, and you can also avoid having to recompute things that you've already visited in the past. So that is one thing you can do. So unless I think of a better idea, I'm probably going to go with that. Zero matrix. So let's look at some examples. Upwards 3, so you start off by flipping the left corner, and then you flip the top left corner, and then you flip the bottom right corner. Interesting. And with 0 because it's already solved, and the third example is given a 1 1 1. Okay. Can't really think of any way to optimize this. I don't really think of any heuristics or techniques we can use in order to figure out what is the ideal solution to use. It really seems to me like the only way to approach this is a brute force solution where we consider every single possibility, and then we fork it off and we solve that problem recursively. And we can use dynamic programming in order to store partial results, and also we want to avoid revisiting the same set if it's already in progress. Okay, so with that said, let's get started. I'm going to create a new package in my little repository that I have. I'm going to call this zero matrix. Flip zero matrix. And I'm going to start off with just a solver. Very unimaginative name, but let's get started with that. So what we have to do is given a binary matrix, so static and min steps needed. And I'm just going to go with a list of a Boolean. And I'm going to say, if this is something we're actually doing in production, create a matrix class. But for now, since this is supposed to be like an interview problem, we're just going to do it the quick and hacky way. We're going to use a list of lists to represent the matrix. The next thing we need is a zero matrix. Just gonna put a to-do here, return false. And you know what? I'm gonna create some helper methods here. I'm gonna call it get rows and get columns. So I'm going to assume that each entry in the top level list represents a row, and so the number of columns would be the size of the first row. To do check that all rows have same number of columns. So I'm going to do that later, or maybe never, but if this is production code, we definitely do want to validate that. And also we want to validate not empty matrix. All right. The next thing we want to do here is to store all the partial results. You can see how this is getting very messy. And that is why I recommended that we create a different matrix class. And with time, we're going to do that, but not right now. You can see that I left a comment, don't make the static. I guess the reason is because in theory, someone could call solver.min steps needed multiple times in parallel, in which case we're going to get all sorts of weird concurrency errors and bugs. We don't want that. So ideally what we want to do is create a new solver class, and we're going to have visited and results as instance variables in the new class. And that way we don't have to worry about any weird concurrency issues. But for now, in order to do this fast, we're not going to worry about that. But we will do that later if we have more time. All right. All right, so the first thing we do, we just check to see if we already have a result, and if we do, we just store it. And so this is going to return, what is it going to return? Returns true if the set did not already contain it. So what should the behavior be if we have visited it? I'm just going to throw a new exception here. In case you're wondering why I changed the ordering, the most common case is that something will be in both the results map as well as the visited set. And if we do have it in the results map, we don't want to throw an exception, we want to actually return the result. If something is not in the result, but it's in the visited set, that means that we're currently in the process of trying to find the answer to that, in which case we will throw the exception. Um, yeah, I think that's right. I guess the reason I'm having a pause here is because I'm thinking that something could be in the visited set. Um, so example, you could go from location A to location B, and then from location B, the only way to get to the answer is to go through location A. Except that when you try to get through location A, it's going to throw the visited exception, and then you're going to say, oh, from location B, I can never get to the solution. That's actually not true, because you can get through location A. But so in terms of reusing the results to solve other problems, this is not going to work. Um, so you know what? We do better reuse across multiple instances. Yeah, I think what I have now, you can't really reuse this across multiple instances because you could end up in a situation where, you start off in A and you're trying to find the shortest distance from A to all zeros. And so you try to get from A to B, and then you try to find the shortest distance from B to all zeros. And it turns out that because B is not allowed to visit A again, you can end up in a situation where B ends up taking a longer route to get to the shortest one. Now, that's fine, because if there's a shorter way to get from A to all zeros, we will just return that. So for the question of how do I get from A to all zeros, you'll get the right answer. But in the intermediate process, you're going to end up storing a value for B to all zeros, which is actually not the optimal route. And so in that case, what's going to happen is that if someone tries to answer a new query, which is how do I get from B to all zeros, and then you try to use the pre-computed value, you're going to end up with the wrong result. So what we're going to do is we're going to create a new solver. And so the static method, all it's going to do is say new solver dot min steps needed for the matrix. I'm going to call this helper. Alright, for some reason my Shift F6 is not working. It's one of my favorite ones. I don't know why it's not working anymore. That is unfortunate. Anyway, let's move on. Alright, so now we found every combination of the row column. So what we're going to do here is we're going to flip. And the way I'm going to do flip is that I'm going to create a new helper function. Flip the matrix, int row, int call. And I'm going to call this flip neighbors without the D. And I'm going to create another helper method called flip. Index is column and the value is updated. Alright. And this might throw a index out of bounds exception. Index out of bounds exception, in which case we will do nothing. So we're going to flip all 4 neighbors. And let's see, we're supposed to flip the original value as well. Yeah, so you say you can choose oneself, flip it, and all 4 neighbors if they exist. Okay, so we got to flip the original value as well. Cool. And if they don't exist, we just don't flip them. So that's all good. And I'll call this flip all because we're flipping not only the neighbors but all of them. Flip all matrix row call. All right. So since we are making a lot of transformations, I don't want to corrupt the original copy. So I'm going to make a new copy. Deep clone. I'm going to clone the matrix. We flip everything. Oh. Oh, this could have been a big mistake. We need to flip the forked matrix, not the original matrix. And then we call it on the get forked matrix. If steps needed is less than min steps, then min steps equals steps needed. So now we get to the end. We found the min steps needed. So we would then populate the min steps into the result set. And you know what? I do not need a concurrent map because I'm no longer making use of concurrency. So results.put matrix and steps needed. Whoa, I don't know where that came from. Min steps, that's what we need. And I guess the other thing we need is that you know what? I have decided. The no result exists should be treated as an integer.max value, not a -1. And the reason I'm doing that is because that allows me to do this steps needed less than min steps check very simply. Because otherwise I'll have to say, if steps needed is less than min steps and steps needed not equals -1, which is a little bit more messy. Is it actually more messy? I don't know, but it seems a little bit more messy. So I'm going to go with this invariant that a smaller value is always the better value. And the max value is the worst value as per that invariant. This seems awfully simple, doesn't it? Yeah, I don't think there's anything left. So we have a static function which all it does is just create a new instance of the solver, and the solver is going to have a results set and a results map and a visited set. The first thing we do, we check to see if the results already has it, and if so, we will just return the result. Otherwise, we would add it to the visited set. And you know what? There should be a false. If it does not add it successfully, then throw a visited exception because it is in the visited set. Okay, so at this point we don't have a result for it. It has not been visited before. So we explore every value that we have in the matrix. And the first thing we do is create a clone because it is not good to mess around with stuff. So once we created the clone, we're going to flip all and then once we flipped all, oh yeah, we need a termination condition. You don't even have a termination condition right now, which is pretty silly, isn't it? You know what? I'm not even going to cache any of the results. Return 0. If it's a 0 matrix, we just return 0. And let me confirm this. Yep, for a 0 matrix, we return 0. That's good. Oh, this is bad. Steps needed plus 1, because we just did a 1 transformation. I think this should work. But you know what? There's actually no way to know whether or not this actually works until I try it out. And so the next thing we're going to do is to try it out. Okay. Let's go to the first example. List of Boolean 0001. False, true. The answer is 3. All right, so now let's solve some compilation errors. Where is my compiler? Somewhere here, apparently. There we go. Return null. All right. This is not TDD, but let's run the test just to make sure it fails, and then we'll go from there. Parsing, compiling, giving me a little breather. And as expected, we get a null pointer exception. Okay, so the first thing we're going to do. I wonder how this works. Construct. I wonder if anyone's ever created a deep copy for a Java collection. But anyway, I wouldn't know. Clone. So I'm going to assume this does not work. New array list. Clone.add list.new array list. So clone the row. Then we add it, and then we return the clone. All right. The next thing is to check for all zeros. And there's my friendly timer telling me to take a break. But I am in the middle of solving a LeetCode problem, so I'm not going to take a break. Is there anything else still pending? We'll find out. That is quite the difference. 3 versus 2 million. What could be going wrong here? Alright, let's find out what does the stack trace look like. You know what? I'm gonna skip past all the visited stuff. Hmm. I wonder if my visited set is somehow tripping me up. So as a little experiment, I'm going to try removing the visited set completely. No, but no, that's not going to work. Because without a visited set, I'm just going to go in loops over and over again. So let's look at the answer. So the first step is supposed to be true, false, true, false. Okay, so we got to true, false, true, false. The next step is going to be false, true, true, true. Do we get to false, true, true, true? False, true, true, true. Alright, so we got to the next step, false, true, true, true. And the one after that should be just false, false, false. Let me just do this. Alright, so we got to the answer multiple times. Huh. I wonder if integer.max value is actually a negative number. Oh, I see what's going on. I'm getting integer.max value, and then you plus 1, and it rolls all the way over to something else. I don't even know what it's going to roll over to. It's going to roll over to the integer.min value, actually. Hmm. Alright. You know what? This is going to now return -1. So if we don't find a solution, -1 plus 1 0. So if steps needed is not 0, and steps needed is less than min steps, then min steps is steps needed. All right, let's see if this works. Well, that's not good. So we got to an answer, but we still returned -1. That should not make any difference at all because it should never be integer.max value to begin with, but let's see. I'm only populating minus ones, even after I got to an answer. Why is that? Oh, of course, I'm a fucking idiot. Steps into the less than min steps is minus one. Oh my god, this is annoying, isn't it? Ah, I'm wasting so much time here. I'm going to break this down because I have a very small and simple brain, so I'm going to make it simple for myself. All right. Let's see. Okay, so now we have found the answer. Let's get off some ugly, ugly prints. All right, so we found that the first two options we tried gave us not very good solutions. And eventually we got the answer. All right, good stuff. So now let's try the other problems. Now we got 4 examples, that's good. One, 101, 000. row 0, row 1, row 2, true, false, true. And false, false, false. False, false, false. And the answer should be equal to 6. All right. Now let's get to the last one. True, false, false, true, false, false. All right. All right. So it looks like I got the answer. Let's do some final review of the solution that we had, shall we? So the first regret that I have is that I never really found a way to reuse the result set across multiple problems. The idea being, we have 4 examples. Ideally, we want to be able to reuse whatever insights we got from example 3 when calculating the answer for example 4. Well, right now we haven't done that because, we talked about the problem earlier where, let's say you have a matrix with location A and a location B, and let's call it matrix A and matrix B rather. And in order to get from A to 0, there may be a pathway, but there's a tangent which takes us to B, and then the shortest solution from B to 0 involves going back to A again, except that because of our visited set, we cannot get back to A again, and because we cannot get back to A, we will actually end up either taking a longer route, or we will declare that a solution does not exist, and this will result in us storing the wrong value for B, and therefore we can't reuse this across different instances of the problem. But within the same instance, that's actually fine, because if the shortest way to get from A to 0 does not involve going through B, then it doesn't matter what the result for B is, because we only care about anything that's on the shortest path, not anything that's on a longer path. And by definition, if the shortest path from B to 0 involves going through A, then the shortest path from A to 0 will not involve going through B. So that is why that is fine. But at the same time, having the partial result set allows us to avoid having to waste time recomputing things. We also need to have a visited set, because otherwise we will visit the same nodes over and over again. Like, for example, we'll go from A to B, and then B to A, and then A to B, and then B to A again. So in order to prevent this pinging back and forth, we need to have a visited set. The second regret that I have is that we have a super ugly list of booleans, when really what we want to do is create a matrix class with helper functions like, flip and get value for row column and all that stuff. So yeah, those are my 2 regrets. But let's walk through the steps. First thing we do is that we have a static function, min steps needed for a given matrix, and what we do is that we create a new solver instance having the map and the set. And then within that, what we do is that we check to see if it's already a 0 matrix, so we just return 0. We check to see if we have a result already, if so we just return the result. And lastly, we populate this matrix into a visited set so that we avoid revisiting it. And when populating it, if we see that it's already present in the visited set, we just throw an exception saying, hey, we've already been here, there's no point coming here again. The next thing we need to do is explore all possibilities. So this is the brute force I talked about, and to be honest with you, I don't know if there's a better way to do this. We got the correct answer. A brute force solution will give you the correct answer, but is it necessarily the best answer? I have no idea. Some person smarter than me may come here and post a comment in the comment section saying, hey, this is actually a better heuristic you can use in order to find the shortest path. And I will look forward to it. But until then, for now, we'll proceed with the brute force solution. So the brute force solution, we initialize the value min steps to the largest possible value, and then we go through every single cell in the matrix. And it's important we actually fork it. And the benefit of forking it is that it avoids interference between my forked matrix and what other children are going to do. Now there's actually one alternative here instead of forking it, because forking is an expensive operation. If you have an n cell matrix, forking it is going to take order n time. And if you're running this operation n times, then you're going to have an n square solution, not an order n solution. So there's actually a to-do optimization. Instead of forking, make all changes, then undo changes later. So the idea being that you keep the same matrix, you flip everything, and then you calculate the steps needed, and then you unflip again. And you got to be very careful when you do that, because if you flip and unflip, and if you don't unflip correctly because of the exceptions or whatever, then you can end up with something very different from what you want to, than what you actually started off with, which is not what you want. So anyway, for now, we're going to do this the simple way. And for every child that we're going to consider, we're going to fork the matrix, and then we're going to use a fresh copy of the matrix for that child. And for that child, we do all the flipping, and then we ask, okay, given this child that I just got from doing one transformation, what is the min steps needed? And then we call our function recursively again. And if we do not find a solution from the child, if we do find a solution from the child, then what we do then is that we will check to see if the solution that we got is better than the solution that we already have. And if it is, we update our current solution with the best solution that we found. And the last thing we do is that we populate the result matrix saying, hey, we found this sub answer, so now you never have to worry about this ever again. And yeah, we probably don't need this either. And then return that. Clone, we're just creating a deep clone, nothing special there. Flip all, we're going to flip the cell as well as all the neighbors. And the flip method, we're just going to get the original value, update it, put it back in the updated value, and then we check to see if there's any out of bounds exception. If so, we just don't flip it, because the problem says if a neighbor does not exist, just do nothing. It's not an error in any way. Get columns, we just get the first row, and then we get rows. It's just the number of rows that we have. And lastly, we check is 0. We just go through every single cell. If anytime we have a true, we return false. If all of them false, then we return true. And there you go, guys. We have now found the solution for a hard LeetCode problem. How do you go from min number of flips to convert a binary matrix into a 0 matrix? Hope you guys enjoyed it.